Find the seismic response coefficient, C sub s. In this problem, a 180-foot office building is constructed of a special steel concentrically braced frame. The design spectral acceleration parameters and 1 second ground acceleration from the maximum considered earthquake are also provided. Using the equivalent lateral force procedure, the seismic response coefficient equals the short period design spectral acceleration, SDS, divided by the response modification factor, R, divided by the occupancy importance factor, I. However, this equation for C sub s has certain maximum and minimum limits. If we call this equation the original equation, then the calculated value of C sub s cannot exceed SD1 divided by T times R divided by I, when the fundamental period of the system is at most the long period for the region. And C sub s cannot exceed SD1 times TL, all divided by T squared times R divided by I, when the fundamental period of the system is longer than the long period for the region. Furthermore, the seismic response coefficient has a lower bound of 0.01, as well as a lower bound of 1/2 S1 divided by the quotient R divided by I, which only applies when the 1 second maximum spectral response exceeds 0.6 G. To solve this problem, we'll first solve C sub s in the original equation. Then we'll determine which of the two maximum bounds apply to C sub s by comparing the period T and the long period T sub L. Then we'll ensure C sub s is at least 0.01 and check the second minimum condition if applicable. The seismic response coefficient equals 0.82 divided by the quotient R divided by I. The problem states the response modification factor equals 6, based on the structure's seismic force resisting system. And the importance factor is based on occupancy category of the building, from table 11.5-1 of ASCE 7. Occupancy categories are defined in table 1604.5 of IBC 2006. The occupancy category for an office building is 2, which means the occupancy importance factor equals 1.00, and the seismic response coefficient in the original equation equals 0.137. Next, we'll evaluate the fundamental period of the structure, T, to determine which maximum condition applies. The fundamental period of the structure in seconds can be approximated as Ct times Hn raised to the x power, where Ct and x are constants based on the structure type, and Hn is the height of the structure in feet, but is unitless in the equation. Therefore, Hn equals 180. Table 12.8-2 in ASCE 7 shows the constant values of Ct and x for different structure types. The problem states the building is supported by a concentrically braced steel frame, which means Ct and x equal 0.020 and 0.75 respectively. After plugging those values in, the approximate fundamental period equals 0.983 seconds, which is less than 12 seconds. Therefore, we'll use the first equation as the upper bound for the seismic response coefficient. Plugging in the values for SD1, T, R, and I, the upper bound of CS equals 0.110. Since the original equation for the seismic response coefficient equaled 0.137, this upper bound is active, and CS now equals 0.110. Checking the lower bounds, the first condition of CS is at least 0.01 and is satisfied. And the second condition is not applicable since S1 is less than 0.6. Therefore, the seismic response coefficient equals 0.110. When reviewing the possible solutions, the answer is C.